Am I recording? Yes, I'm recording. Oh. Okay. So here we go. Question 1. Which of the following best describes a racemic mixture? So do you guys know what a racemic mixture is?
I don't.
So
No.
I don't think you guys talked about this yet in class, but it's not nothing too bad. What a racemic mixture is D. It's a mixture containing equal amounts of enantiomers. And enantiomers are molecules that are chiral, meaning they don't have a mirror imaging of themselves. They're non-superimposable. So racemic mixtures have an equal amount of enantiomers that are made in the product. That's all it is. All right. So let's go to 2. Which of the following statements about a cyclohexane chair conformation is true? So A says there are 12 equatorial hydrogen atoms. Is that correct?
No.
No, that's not correct. We draw the chair conformations, you know you have up carbons and down carbons. So on the up and downs, you will have axial hydrogens, like so. That's 6. And we'll have equatorial hydrogens on, like down equatorial on the up carbons and up equatorial on the down ones. Trying to draw it in, it's kind of difficult. 2, 3, 4, 5. Missing one somewhere. Where am I missing? Oh, I think somewhere here. There. So when you have your cyclohexane chair conformations, there's supposed to be 6 axial hydrogens and 6 equatorial hydrogens. And the answer choice that matches that is E. Any questions so far?
No.
All right. So 3. Which of the following is least able to serve as a nucleophile in a chemical reaction? So what is a nucleophile? Who remembers what a nucleophile is?
I don't know, but it can don't go into electrophile, like donate it, something.
Yeah, it will donate its non-bonding lone pairs to an electron-deficient species. So a nucleophile are electron-rich species, or compounds or molecules, however you like to say it. They're electron-rich. So we have answer choices here. A is Br minus, so this is what it is. B is NH2 minus, which is this. C is CH3 plus, so that's this. Carbon has a positive charge. D, oops, I switched C and D.
Yeah, so
So this is D, and C is NH3. That's this species. And last is E, which is your OH minus. Another word for it is hydroxy. So out of all these molecules drawn, which ones would not be a nucleophile? It's not electron rich.
D.
Right, D. Atoms with a positive charge are definitely not electron rich. They're very electron deficient. And carbon is very famous for being electron deficient. All the other species you see here, they have lone pairs to give into a bond. So that makes the rest of them electrophiles. So the only one that it isn't, not electrophile, nucleophiles, I mean. The only one that isn't a nucleophile is D. Any questions?
No.
All right. So 4, which of the following molecules is chiral? You guys talked about chiral molecules yet?
No, I don't think so.
Okay.
No.
So I'm gonna just give you a little heads up on chiral molecules. Chiral molecules are molecules that have stereogenic centers. So we did talk about stereogenic centers, and what that is it's a carbon with 4 different groups attached to it. So let's say you have a OH, you have a H, you have a bromine, and then you have, let's say, a methyl CH3. This carbon is stereogenic because there are 4 different groups around it. Because of those 4 different groups, this molecule would be non-superimposable because stereogenic centers have what we know is R and S conformations. So once you start giving the bonds properties, like bromine will have first priority because it's, a bigger atom. The alcohol has second priority, oxygen is more electronegative. The methyl has third priority, and then the least priority is 4. So when you count it, 1, 2, 3, it's going in kind of like a counterclockwise motion, right? So that's an S conformation. So if you try to flip it as if it was a mirror image, the conformation changes. And because of that, it cannot be superimposable. It's non-superimposable, which makes it chiral. So out of each of these answer choices, which one of these molecules do you know have stereogenic centers? Can it be B, for example? Right, A. Both of these carbons have 4 different groups attached to it. B, they have the same type of attachment, both carbons, so they're achiral. That's the opposite. Same thing for C, and same thing for D. So A is a chiral molecule. Any questions on chiral?
Oh, yeah, I don't understand this question.
So when a molecule is chiral, the carbons in the center, they're stereogenic, meaning, for example, how I drew this carbon here with 4 different groups around, like an alcohol, a bromine, a methyl, and a hydrogen. This is what's known as a stereogenic center. It's chiral because with stereogenic centers, the kind of conformation you come up for them to understand their stereochemistry is called R and S. The way we do that is we give the groups priority based on the periodic table, like atom size or electronegativity. You use those trends to help you with priority. So bromine gets first priority because of its atom size. It's bigger. So that's 1. The OH, that's second priority because oxygen is an electronegative atom. It's definitely more electronegative than the carbon in the CH3, the methyl. So that's why CH3 gets third priority, and the least will always be hydrogen. Now, if you count from 1 to 2 to 3, like if you do the hand movement, you'll see you're kind of going counterclockwise. This has an S conformation. But if you try to do it, let's say you try to do it the other way. So I'm gonna do it like this: C, B, R, O, H, H, and CH3. Priority still the same, doesn't change. So 1, 2, 3, 4. Now, if you go 1, 2, 3, like do the hand movement for the other side. How is your hand moving? Clockwise or counterclockwise?
Clockwise.
Yeah, it's going clockwise now. So now the conformation changes. It's not S anymore, it's R. R is clockwise. So because of the change of conformation, this cannot be what's the other word for achiral? This is chiral. If there was no change in the conformations and the molecule was exactly the same on the other side, then it would be superimposable, but it isn't. This is non-superimposable. So non-superimposable molecules are chiral. Did that help?
Yeah, thank you.
No problem. Let's move on to the next question. So, 5. Sorry for coughing, this cold weather is killing. Which of the following is the most stable conformation for trans 1,4-dimethylcyclohexane? So we're looking at all these different chair conformations. So what do we know about the stability of chair conformations when it comes to different substituents attached to it? Where are they more stable?
In equatorial?
Right, they're more stable in the equatorial positions. So the more you have these substituents in the equatorial positions, the more stable the chair conformation. So which of these answer choices would be more stable?
C.
Right, C. Both methyl groups are in the equatorial position. That makes this chair conformation even more stable than the rest. Any questions?
No.
6. What kind of reaction is shown below? So what's happening? This is your product. This is the, that's a product. This is your reactant. And this is your product. So what happens?
The double bond disappear.
Right, so we've broken the carbon-carbon double bonds, and as a result, what happens? What do we see?
A bond between carbon and Br and
Right. So carbon bromine and a carbon fluorine bond has been made. So this type of reaction, do you think is substitution?
No.
No, we're not substituting anything in this reaction. So it cannot be substitution. What about elimination?
No.
No.
No, definitely not elimination. We didn't eliminate a atom from this molecule in this reaction at all. So it can't be elimination. You guys didn't learn acid and base yet, but it's definitely not acid base because what this reaction deals with is with protons. In other words, it deals with the hydrogen atoms a lot. In this case, we don't see nothing between, like no bond breaking or making between CH or any other atom with hydrogen. So it cannot be acid and base. So the answer is D. Whenever you go from a double bond in your reactant and it's not there no more, you went from an alkene to an alkane, that's an addition reaction because you're adding molecules. You're adding atoms onto the molecule and breaking that double bond. So this is an addition reaction. Okay. Next question. List the following substituents in order of increase in priority. So from lowest to highest. So when we're dealing with priority, what we like to do when given molecule priority, we like to use the periodic trends for this. So the first trend you would pay attention to is like the atom size, because atom size has a very huge effect on electron energy. The bigger the atom surface, the more electron energy you're going to have, which is even greater than a more electronegative atom. So you want to look for if you have very big atoms as your choice first. Then you want to pay attention to electronegativity. So this is how you would do priority. From electronegativity, you go to like the size of the groups, but that's normally when you have like a buildup of carbon as your substituents, like the tert-butyl, it's a big group, so you'll get that higher priority than like a methyl, stuff like that. So here we have a methyl, ethene, you have the bromine, you have an alcohol, the CH2OH, and you have the CH2NH2. So We're going from lowest to highest. So which molecule here would have lowest priority?
The metal.
Right, the CH3. CH3 would be lower. After the CH3, what do you think comes next?
I don't know. That's not an ethyl, so CH with double bond with CH2.
Wait, give me 1 minute.
The second one.
Oh. Hold on. I thought I think I made a mistake. Oh no, I didn't make a mistake. So the double bonds is kind of, it's an exception because double bonds have very high electron energy with that pi bond, and the pi bond is very reactive. So that would be more on the increase in priority side. So after the methyl is actually the CH2OH. And after that comes the CH2NH2. Now, why do you think the nitrogen comes after the oxygen here, even though oxygen is more electronegative? Why do you
Because as electronegative increases, size decreases.
size does decrease going from down and up on the periodic table, but what I want you to pay attention to is this NH2 attachment at the end here. That means that nitrogen has what?
A plus charge.
It means it has a lone pair. This nitrogen has a lone pair. And lone pairs on nitrogen are very high in energy and reactive. And since oxygen here is very electronegative, its reactivity is not so high. So this is lower in energy than nitrogen. Molecules that are also higher in energy, they have higher priority. So that's why the NH2 attachment to the carbon comes after the oxygen attachment. Any questions on that? If this was an NH3, it would have been flipped because then the oxygen is more electronegative. So after this, then it comes the carbon-carbon double bonds because it's very reactive. And lastly, your highest priority would be the bromine because it's the biggest atom. So the answer choice that matches that is C. Any questions? Let's move on to question 8. So 8, consider the following bonds. You're looking at a fluorine hydrogen, chlorine hydrogen, bromine hydrogen, and iodine hydrogen. So obviously we're looking for which of the answer choices are true. Again, you don't know about acidity or basicity, but let's not worry about this part. Let's focus more on the beginning part of the choices here. So A says chlorine hydrogen has the smallest bond dissociation energy and is the most acidic. Is that true? Oh, do you think that's true?
No.
It's not true. The chlorine hydrogen molecule here doesn't actually have the smallest bond dissociation energy. Another molecule does. Because we see a molecule that's much bigger than chlorine here. So B says FH has the smallest bond dissociation energy, is the most acidic. Do you think that's true?
No.
No.
No. FH, that's a very strong bond. Fluorine is very electronegative. So because of that electronegativity is making the bond stronger. So you're going to need a lot of energy to break that FH bond. So it's not the smallest bond dissociation energy. That's also not true. C says IH has the largest bond dissociation energy and is most acidic. Could that be true?
No.
No, you're right. It's not true. IH is a what bond? Strong or weak?
Weak.
Right. It's a very weak bond because the iodine is a huge atom. So what's happening is it's stretching that bond, and that bond stretch is what's making it weak. So it doesn't need a huge amount of energy to break. You can give it a small energy and it'll just break just like that easily. So it can't be C. It can't be D neither. FH does have the largest bond dissociation energy, but it isn't the most acidic. You'll learn the trends with acidity on the periodic table too. And acidity actually, where does it increase? I think it increased from right to left on the right to left. I believe so, but you'll learn the trends. The answer choice here is E. IH has the smallest bond dissociation energy and is the most acidic. So what you will learn with acid and base reactions is that because we're dealing with the protons, which is the hydrogen bonds, a lot in acid and base, the molecule that is more willing to give up its hydrogen atom would be the most acidic. So because IH is a very weak bond, it'll give up the hydrogen atom very quickly and better than FH because that's a very strong bond. So this would be a more acidic molecule. Any questions? Let's move on to 9. So what is the IUPAC name of the following compounds? So as you look at the answer choices, you see R and S. That's because we do have 2 stereogenic centers in this molecule. This carbon is a stereogenic center and this one. So we have to give it its correct conformations. So when we start numbering the carbon chain, right? First, let's find the longest carbon chain. What would be the longest carbon chain in this molecule?
5.
Right, 5. 1, 2, 3, 4, 5. 5 is the longest carbon chain. So the ending name for it would be what?
Pentane.
Right. Pentane. Then you have your substituents. You have bromine, you have chlorine here, and you have these 2 methyls over here. Now, let's number the carbon so that when we include the number in the name, it's correct. Will we start numbering from the left or from the right? What do you think?
It doesn't matter, but start from the left.
Now, it wouldn't matter if we were dealing with methyls because they have same electronegativity and all that. But in this case, this is where it matters now. Because bromine is bigger than chlorine because it's lower on the periodic table.
Mhm.
The priority matters for when you're numbering the carbons. So you have bromine, which is a bigger atom. Like the bigger atoms and the bigger groups and the more electronegative substituent, etc. and stuff, you want those to be on a smaller number of carbons. So you actually start numbering left to right. So 1, 2, 3, 4, 5. Any questions?
No.
All right. So now we know R and S has to fall into the naming because we do have stereogenic I almost said chemistry carbons. So let's look at this first carbon here that I marked in blue. What group has higher priority? Which substituent on this carbon?
Bromine.
Right.
Bromine.
Bromine has higher priority. Next would be what? What do you think?
The hydrogen.
So hydrogen's always given low priority because it's a very small atom with very little electronegativity. So that always given priority for. Hydrogen's is always given the least priority. The second priority, however, would be this attachment here. How this carbon is connected to this carbon with the two methyls, that would be higher priority because that's kind of a big carbon group. So that'll be 2. And then third priority would be given to this little methyl over here. Anyone confused with that? All right, so you have the priorities. Now, when you count in the priorities, 1, 2, 3, 4, are you going clockwise or counterclockwise?
Clockwise.
Yeah, you're going like this. So on carbon number 2, it'll be R. It'll be R. So now, let's do a different color. Let's look at this carbon over here. So higher priority goes to what?
Chlorine.
Chlorine.
Mm-hmm. It'll go to the chlorine over here. Then comes what?
Could you go back to the like?
The methyl group.
The what?
The methyl group.
Oh, so it won't be the methyl group. It'll still be over here, this whole attachment here,
Yeah, I was asking.
because you have a carbon connected to a lot more of the carbons. So yeah, you was correct. It goes back to you give this second priority. Then third will be the methyl here still. And then fourth, always the hydrogen. So now you go 1, 2, 3, 4. Are you going clockwise or counterclockwise?
Counter.
This time you're going counterclockwise. So 4 would have conformation S. Now we have to include that in the naming. So it'll be 2 R 4 S. Remember your naming alphabetically. So what substituent would we do first?
Chlorine. C.
Bromine.
No, bromine.
B comes before C. So 2 bromo.
Oh.
That's all right. It's very easy to miss. I almost did the same thing just now. 4 chloro. And then you got 2 methyls on carbon number 3. So 3 dimethyl pentane. So the answer choice that matches that, B.
No,
On the
there's 2R on B.
oh, oops, I didn't mean to say B. Just notice the B. This one says 2R4S2. I think there's a typo in A. 2 is supposed to be R, and 4 is supposed to be S. It's not supposed to be 2S, 4R. It's supposed to be 2R, 4S.
Okay, that makes sense.
Yeah, I'm a text man about that because there are a little bit of typos. Because last one of the practice exams I went through, there was a little typo as well. So I'm gonna just check back to him on that. But it is 2R, 4S, 2 bromo, 4 chloro, 3 dimethylpentane. So I'm gonna skip 10 because you guys didn't do acid and base yet, and I want Ben to explain that reaction. Oops. So let's go to 11. What is the relationship between the following molecules? So, A, enantiomers. Remember, enantiomers are molecules that are chiral. And for chiral molecules, they have to have what?
R and S conformation?
Yeah, they have to have stereogenic centers. So, can these two molecules here be enantiomers?
No.
Right, no. Looking at it, you have two of the same type of groups attached to the carbon. Whenever you have that, it is not stereogenic at all. You always have to have 4 different groups around a centered carbon. So they can't be enantiomers. Diastereomers now, those are molecules that show you cis and trans. Are any of these molecules cis and trans? Like, is one cis and is one trans?
No.
No. Both of them have trans substituents on it. So neither one is just cis. The other one isn't just trans. So that's why they're not diastereomers. C says constitutional isomers. Who remembers what a constitutional isomer is?
Same number of carbon.
Mm-hmm. So same molecular formula, but what?
With different conformation.
Right. And with the different conformations becomes the different names. Do these look like they're attached in different ways to be constitutional isomers?
No.
They just
Right.
flip.
The thing is, when it comes to identifying constitutional isomers, how this looks flipped, it would not be considered a constitutional isomer because if you were to like number the carbons and name them, you get the exact same name. That's why whenever you're dealing with these constitutional isomers, you never try and draw a flipped version of the molecule because you're just drawing the same exact thing. So they're not constitutional isomers. And do they look like different compounds?
No.
No, they look exactly the same. So the answer is E. They're identical. Identical compounds. Any questions on that?
No.
We'll skip 12 because you'll learn about pKa later on in the lectures. So 13. How many stereogenic centers are present in the following molecule? So let's look at every single one of these centered carbons. Can this carbon here be stereogenic?
I forget what stereogenic.
No.
So stereogenic is when a carbon has 4 different a centered carbon has 4 different groups around it. So I'm gonna put up an example, like OH, Br, H, and CH3. 4 different substituents on the centered carbon makes it stereogenic. This top piece, this carbon I dotted though, is not stereogenic. We have the same type of groups attachment twice. So because of that, stereogenic is out of the table. What about this carbon here?
No.
No, you have 2 hydrogens. Because you have 2 of the same group, not stereogenic at all. What about this one?
No.
Right, no, same thing. How about this carbon? Can it be stereogenic?
No. We have.
The answer is yes. So the reason why is because all these carbons are kind of connected in this chair conformation, you have to look at like the continuation carbons and how they're connected. This way, the carbon is connected to a ketone. This way, the carbon is connected to this weird looking carbon group over here. Going up is connected to a different carbon attachment as well. And the last attachment has to be a hydrogen because we only see 3 physical bonds there. So hydrogen. So it does actually have 4 different groups around this carbon. So that's why it's stereogenic. When it's in this type of attachment, you have to pay attention to how they're connected on each side continuously on the chain. If there's any difference with the sides and all that, like how the ketones over here there isn't one, and how the carbons up here is attached, it's stereogenic. So can this carbon be stereogenic here?
No.
Nope. 2 same groups. What about this one with the ketone?
No.
No. Stereogenic centers definitely cannot have double bonds. That'll take away stereogenicity or however they say it. So definitely not stereogenic. Now, what about this carbon back here?
Yes.
Yeah. It does have 4 different groups. Next to it, the carbon is attached to the ketone. Next to it, this carbon is attached to other carbons. Going up, the carbons are attached to other carbons in a different way, and then it has a methyl attachment here. So 4 different groups. So you have how many stereogenic centers in total?
2.
Right, only 2. Any questions with this question?
So the first stereogenic will be the green one, and what's the other one?
Oh, the red one in the back here. Let me highlight it with this pinkish. So this carbon in the back here too. That's stereogenic.
Okay, thank you.
You're welcome. Any other questions before I go to 14? Okay. So, what is the IUPAC name of the following molecule? So, you have a Newman projection here. What is this Newman projection representing?
A chair.
It's representing a chair conformation. Now, how many carbons are connected in this ring? Remember, these are carbons
6.
here as well. Right, 6. 1, 2, 3, 4, 5, 6. So we're looking at a cyclohexane. So cyclohexane is the last part of this naming. Now, we know the longest carbon chain is 6. So 1, then 2 is this big one. 3, 4, 5, 6. we have a bromine substituent here and a bromine substituent here. So when we're numbering the carbons, we want to give the substituents small numbers, right? So anywhere you start from any of the carbons with the bromines, it doesn't matter because it'll be 1, 3 all the time. So you can do it left or right. So this intersected carbon in the front here, that'll be 1. Then this one is 2. This one is 3. The big one in the back of this one is 4. This one's 5. And the big one back here is 6. Any questions? So now you have bromine on carbon number 1 and carbon number 3. Now, both the bromines are facing the same way. So what do we have to include in the naming?
Cis.
Right, cis. They're both pointing down. So there's cis. So cis 1,3 dibromocyclohexane. And the answer choice that match is A. Any questions? So when you get a question like this and it's with the Newman projection, first you want to see what carbons your substituent is located on. You need to be careful because sometimes you could get a substituent on the big carbon instead of just the front intersected one. Then, of course, you number accordingly because you want it to fall on a small number carbon. Then you name your molecule. Be sure to see whether the groups are facing like both down, both up, or one's going up, one's going down, because cis and trans can be included. All right. Let's go to the next question. Question 15. What is the configuration on molecule 2? So we're not paying attention to one, we're paying attention to this one. So we're looking for the configuration. What exactly are we looking for? Whether it's what?
Stereogenic.
Right, they're stereogenic carbons. So we're looking for the conformation. Is it R or is it S? Let's find out. So before we do that, we have to give priorities to the substituents that are attached to this carbon. So we have a carboxylic acid. That's what this Q is. It's a carboxylic acid. You have an alcohol. You have I think this is an amine, right? And then you have, of course, your little hydrogen. So which group has higher priority? What do you think?
The amine with a lone pair?
So actually, what will have higher priority would be your carboxylic acid. You have, two oxygens, more electronegative, and then resonance can happen between them, so higher priority. Then what do you think comes next?
The amine.
So what actually comes next is your alcohol here. And then comes the amine. So we're not paying attention to the lone pair on amine. We're more focusing on the whatchamacallit, electronegativity. Sometimes priorities is weird. And then fourth, of course, is always your hydrogens. So when you're counting your priorities, 1, 2, 3, where's your hand moving? Clockwise or counterclockwise?
Counter.
It's
Counter.
going counter, right?
So it's S.
We would think it's S. Here's the thing these scientists love to do. I don't even know how Ben figured this out. Like, I need to ask him. So it's saying here that in the key, it looks like S. But what happens is it's actually going R because this H is supposed to be coming towards us. So this is supposed to be in a wedge. That means the nitrogen here is going to be on the dash. So because the nitrogen is being pushed back, you go like 1, 2, 3 because of how that nitrogen is back, and it's going R. I believe you guys will learn. He didn't teach you about that yet, right? How sometimes it looks like it's R or S, but it can be the opposite.
No.
Well, he should have gotten to that when you guys started speaking about the stereogenic centers, because sometimes depending on where the low priority atom is, which is most likely a hydrogen, if it's coming towards you, it's opposite. If it's going away, it can make it opposite as well. It's kind of weird. That's why I don't really like stereogenic centers too much. Like, who wants to deal with that? All right. Question 16. What is the relationship between the following molecules? So, can they be stereoisomers? So stereoisomers deals with trans and cis molecules. Are each of these molecules stereoisomers to one another?
No.
No. All of the fluorines are facing opposite directions, so each one of these chair conformations is trans. So because it's only showing a trans conformation, it's not stereoisomers, because in order for it to be stereoisomers, one has to be cis and one has to be trans. And plus there's 3 molecules here, so they're not stereoisomers. What about B? Can they be constitutional isomers?
No.
No. If you number your carbons accordingly to where the substituents is, you will see that both fluorines actually fall in the same carbon. So on the first one, 1, 2, 3, 4. On the second one, you number from here, 1, 2, 3, 4. And on the third one, you can go from the back of the front. So 1, 2, 3, 4. They all land on 1, 4. And because of that, they're going to have the exact same name. So they're not constitutional isomers. And because they're the same, they won't be different compounds. They're identical. Any questions?
No.
Let's move on to 17. Which chair conformation of cis-1,3-dimethylcyclohexane would have the highest heat of combustion? So when we're asking highest heat of combustion, we're looking for what? How can that relate to the stability of a molecule?
The higher stability.
So in other words, the molecule that would have the highest heat of combustion, would it be stable or unstable?
Unstable.
Yes.
Right. It would be a very unstable molecules. So molecules, whenever they react and they release a huge amount of energy, they have to be in their unstable conformation. So we're looking for the most unstable molecule. Which of these answer choices would show an unstable molecule? What do you think we have to pay attention to?
The methyl groups, if they're in equatorial.
Right, exactly. So we know they're more comfortable in an equatorial position. That's how they'll be more stable. Now, since we're looking for the most unstable molecule, we want these methyls to fall in what position?
Axial.
Exactly, axial. So which of these answer choices have the methyls in an axial position?
B.
Right. B. It has both methyls on the axial, so they're pretty close together, which is going to cause steric hindrance. And steric hindrance always pushes the molecule to be unstable, because what that means is electron repulsion between the electron energies of these two groups because of how close they are together. It's like trying to force two magnets that on the same side together. They're never going to come together. All right. Let's move on. I'll skip 18 because I don't know what that is. I don't even know if you guys would do a problem like this on the exam. So 19. Which statement is correct concerning the relative stability of the two conformations 1 and 2 below? So in both conformations, we have a methyl that's going equatorial and a methyl that's going axial. They both fall on the same carbon, of course, because what's happening here is a ring flip. And they're both facing opposite from each other, so that means they're trans. So what can be said about their stability?
The same.
Right. Their stability energy isn't different. They're both the same. Because they're trans, they're going to be more stable. And one of the groups fall in the equatorial position. So it's cool. Both chair conformations have equal stability. All right. Let's go to a question that I want you guys to see. Let's go to 21 before time's up. So, determine if each of the following pairs of compounds represent enantiomers, diastereomers, constitutional isomers, same molecule, or different molecule. So, let's look at the first one first. Let me just number it. 1, 2, 3, 4. Let's look at the first pair. The best thing to do is to figure out if the molecules are constitutional isomers. That's like the easiest thing to point out. So, how many carbons are in this cyclopropane?
3.
Right, 3. 1, 2, 3. So now you also have to count the number of hydrogens. So how many hydrogens are in this molecule? This carbon has how many?
2.
Right, 2. This carbon has how many?
2.
This carbon has?
1.
Right. And you also have to include the hydrogen on the oxygen. So we know we have 3 carbons, and now we have 2, 4, 6 hydrogens. So this first compound has C3H6. Now, let's check the second molecule. How many carbons?
3.
Right. 1, 2, 3. These carbons are connected to the oxygen, so there's only 3 carbons. Now, each of these carbons have how many hydrogens attached?
6.
Two.
Well, 2.
Right. 2 or 6. So this is also C3H6. Now, we can tell that they're not identical, right? Because they have the same molecular formula, but one has a cyclopropane, while the other one is just a cyclic structure with an oxygen. as one of the ending attachments. So that means they're what?
Constitutional isomers.
Right, constitutional isomers. So we'll put C in this box. Now 2. What do you think these are? They look like they can be the same. And however, down here, we just have a hydrogen instead of the alcohol like the first molecule does. And we have an oxygen in the ring structure. So that means they can't be what? Do you think they could be constitutional isomers?
No.
No, because now the carbon number has changed, especially since we have an oxygen in the cyclic structure on the second molecule here. So they can't be constitutional isomers. They're not diastereomers because it's not cis or trans. They're both cis. It's both a cis molecule. They're not they're not enantiomers because there are no stereogenic centers in none of these molecules. So they're different. It's going to be X. Any questions? All right, so it's 6 o'clock. You guys could try and do the other 2 on your own. And if you have any questions, you could email me. I see that Ben put that the exam is on the 10th of November. So as you keep joining my office hours, we're still going to be looking